In this video, I'm going to derive the equation for refraction called Snell's law. Part of the derivation requires us to use wave fronts, so I'll define those wave fronts here. A wave front is a point on a wave with the same phase. Now, what I mean by that is if I connect together all points on a wave with the same phase in 2 dimensions, it forms a 1-dimensional line. If I have a 3-dimensional wave, then my wave fronts will form a 2-dimensional surface. So here I'm looking at a 2-dimensional wave, and I draw a dot wherever I have the same phase, and I form these lines. In this graph, the displacement is in the y-axis, and we are looking at an instant in time, so we can see the variation of displacement as a function of the x-axis. The z-axis is this second spatial axis giving us our 2 dimensions. The general wave equation is that displacement is equal to amplitude multiplied by the cosine of the phase, which here I'm calling theta. We have to be a bit careful because we will be using theta later on, so you can call it a different letter if you prefer, but I tend to call the phase theta. The phase, at an instant in time, is equal to 1 full oscillation, 1 full cycle, 2 pi radians, multiplied by the fraction of that oscillation. So the phase at position x will be equal to 2 pi multiplied by x divided by the wavelength. The wavelength is the distance between 2 wave fronts in a direction perpendicular to those wave fronts. You can see that when x equals lambda, so we'll start here where our phase is, let's say, 0, then if we move in the x direction 1 wavelength, then x divided by lambda will equal 1, and the phase difference between this wavefront and this wavefront is 2 pi, which is equivalent to 0. So that's how phase works. And that's what wavefronts are. So now we can use wavefronts to construct a diagram of refraction. So here are our diagrams. On the left is a diagram showing the wavefronts moving perpendicular to the wavefront, so the ray is indicated with this blue arrow here, moving towards some boundary. Now, if this is an optical system, this boundary may be the boundary between 2 media of different optical densities. But this could be water waves, and this could be some step in the depth of the water, changing the speed of the water across that region. As we saw before, the distance between 2 wavefronts is equal to 1 wavelength. Now I've labelled one medium, medium 1, and I've labelled the other medium, medium 2. So I'm considering this from an optical point of view. Refraction does happen in other wave systems, but we're going to consider it purely from an optical point of view. So the ray enters perpendicular to the wave fronts and refracts. You will notice that the wave fronts are at a different angle to the wave fronts that entered. The incident ray and the refracted ray are travelling in slightly different directions. And it could be that the refracted ray bends the other way. That's okay as well. Snell's law can handle both situations. So I've drawn the middle part of this diagram larger here. And you can see I'm only focusing on the wavefront just before the boundary and the wavefront just after the boundary. I've labelled the incident ray over here on the left for convenience, but of course the incident ray is at any point perpendicular to the wavefront. There are incident rays all the way along this wavefront that I'm not drawing. The same is true for the refracted ray, which is travelling down in this direction in this diagram. Now, because the wavefront and the ray are always perpendicular, then the angle the wavefront makes to the boundary is equal to the angle the incident ray makes to the normal. And the angle that the refracted wavefront makes to the boundary is equal to the angle that the refracted ray makes to the normal. I've labelled the angle of the incident ray theta 1 because it is the angle within medium 1. And I've labelled the refracted ray's angle, the angle of refraction here, theta 2, because it is the angle in medium 2. You'll notice that we have triangles set up. And these triangles share a hypotenuse, which I've labelled here h. This shows why it's so important to always measure your angles of incidence and angles of refraction from the normal. That's part of the derivation of this equation that we're looking at today. So we can use our knowledge of trigonometry to write an expression. Sine θ1 will equal the opposite, which in this case is λ1, divided by the hypotenuse, which I labelled h. Sine θ2 will equal the opposite, which is λ2, divided by the hypotenuse, which is h. And I've written those two equations here. Sine θ1 equals λ1 divided by h, and sine θ2 equals λ2 divided by h. I've rearranged each of those equations to get h as the subject, as you can see below here. And as h is the same for both of these two equations, they are simultaneous equations, so I can equate them to get this expression here. λ1 divided by sine θ1 is equal to λ2 divided by sine θ2. So I've just scrolled down so we can see the rest of this derivation here, and we need to define the term refractive index now. So this is for optical media. A refractive index is the ratio of the speed of light in a vacuum to the speed of light in the medium. I've used the subscript m here to indicate the medium. So n subscript m is the refractive index in medium m. C subscript m is the speed of light, in this case, in the medium m. And an equation we have for the speed of a wave is frequency multiplied by wavelength. So we can say that the speed of the light in medium m is equal to the frequency of light in medium m multiplied by the wavelength of light in medium m. Now, importantly, the same number of waves per second are incident on that boundary as pass through the boundary and are refracted. Therefore, the frequency is exactly the same for the waves in medium 1 as it is for the waves in medium 2. The refractive index in medium m can therefore be written as C0, which we have from this expression, divided by, and then f lambda m, because we're substituting this expression for Cm. And I've dropped the subscript m from the frequency because it's the same for both media. Rearranging this equation to get the wavelength as the subject, we get this expression here. I can now substitute this expression into our equation up here, where m can take the value 1 or it can take the value 2 for the two different media. Substituting this expression into here gives us this expression here. I've separated out the C0 over f because C0 and f is the same for both media. C0 is the speed of light in a vacuum, so it's independent of the medium, and f is the frequency, which, as we've discussed before, does not change as the wave passes through that boundary. This means that we can cancel out the C0 over f from both sides. And if we take the reciprocal of the 1 over n1 sine θ1 equals 1 over n2 sine θ2 that we're left with, we arrive at the expression for Snell's law. This is a very special expression because it doesn't matter whether medium 1 is more dense than medium 2 or medium 1 is less dense than medium 2. This equation works either way around. So you don't have to keep track of whether or not you have refraction from a less dense to a more dense medium or vice versa. The equation can handle it either way. Well, I hope you found that helpful. If you did, please do share this video with other people who might find it helpful. Like the video. If you subscribe to it and ring that bell, you'll be notified when more videos are released, and you'll also be notified when I go live for my weekly tutorial sessions. Thank you.